So today's topic is somewhere in section 2. And so the overall chapter here is tasks in quantum information theory. And so I'm putting together several standard tasks of computation. And the common feature is that they can be solved by semi-definite programs, and then we'll talk about semi-definite programs. Right? So some semi-definite problems, I think semi-definite tasks. Okay. So I'll begin by just describing what a semi-definite program is. So would be something like minimize with respect to variables, let's say x1 to xn also. And the target functional that is to be minimized is just a linear functional. The interesting part are the constraints. Right? Subject to so a certain matrix that depends on x and is just an affine function. So where f naught, well, up to n, right? Permission matrices. Okay, so the basic, this is just saying that we are really looking at a set of matrices, and they have a linear or an affine, to be more precise, an affine parameterization. That is, they lie on some lower dimensional manifold, possibly lower dimensional manifold, so n-dimensional submanifold in the space of matrices. So here we have the cone. And so this is the plane that we're looking at, and we are cutting out some piece from that. My perspective is not very good, but think of that. So for this kind of cone, it would of course be an ellipse, and on that intersection set here, we would like to minimize the linear function. Of course, we can take the c's negative, and then it would be maximization. It doesn't really matter. Okay, but the point is that the constraints are given by positivity of matrices, and this is why it's called semi-definite. I mean, this relation says that this matrix is positive semi-definite. We just say positive because it happens all the time. So this is the cone that chapter 1 was completely about, if you want. So we know quite a bit about it, and it is quite natural that many problems in quantum information are actually semi-definite programs, because if I have to optimize some linear target functional for states or observables, automatically my constraint will be this kind of positivity. Right? So this happens all the time. So there is a variant of that. depending on how I write these matrices, or what the matrices are, there might actually not be a solution X, right? So any X, so that this is possible. So is there an X with So this is sometimes, for example, if I'm looking at the existence of a joint measurement for two observables, I have to find the matrix, the POVM elements of the joint measurement. And the only constraints I have for that is that they have to be positive, right, and add up to, so the marginals come out, right? So I didn't mention linear constraints, but I'll do that next, right? So is there an X? So it turns out that this is the same thing. And you can solve it like this. You throw in an additional variable that you could call the infeasibility, and you're minimizing S. So the target functional that you want to minimize is the infeasibility, and subject to So, of course, if you this is the same data, right? So if you ask for feasibility, what this does is, well, certainly if you given the x's, you just given any old x, right? You compute this, and these are finitely many matrices, so there is a lowest eigenvalue, and if you add that much of the identity, then of course you get something positive. So it's clear that there are feasible tuples x and s. Actually, for every x there is an s, so that this is feasible. So so then you have the same sort of problem. It's another semidefinite problem where feasibility, the existence of a feasible point in the first place, is guaranteed. Right? Okay, so and let me just remark on this. I'll keep this part because we'll come back to that when we come to the dual problems. This is then called the primal problem, and there's always a dual semi-definite program, and we'll come to that later. But linear constraints are given by, let's say, g of x, another such affine function, and g of x. Right? So the way to enforce that is to take a matrix F g minus g and ask that this is positive, and then automatically you have made a linear constraint. Huh? Okay. So this is why I have only this inequality constraint, because that's easier to have only one constraint, one type of constraint for the theory. But of course this includes also linear constraints in addition. Okay, so examples. Separating. And this would be some tasks, computational tasks, where you, let me just jump into it. So a very elementary one is unambiguous state discrimination. So in the early 2000s, you find tons of papers about this. Yeah, quite a few. So, and the task here is given are two states. So, you know that a preparing device either produces this state or that state. For example, somebody could use that for signaling, and the two values on a bit string would be encoded by preparing one state or the other, and these states are known. Right? So, so you're supposed to find an observable with POVM elements F1, F2, and F0, where 0 means don't know. So you're supposed to design a measuring device that does the following. If it can give three different results, 1, 2, or don't know. And 1 just means that you're guessing that row 1 was presented. And 2 means that you're sure that row 2 was presented. And 0 means that you can't decide. Of course, you can always solve this by always saying don't know. That would be boring, so that so we know that these are positive, right? So if I are positive and sum of I is 1, that means they are an observable together. And you would like to minimize the probability of having to say don't know. And a reasonable target for that would be to think that the two choices happen with equal probability. And this is then, under such conditions, this is the overall probability of having to say don't know. Right? And this is what you want to minimize. Okay? Yes. And you also have a linear constraint. Sorry, that's the important part. You should never be wrong. So if it was actually the state 1, then you want to be sure that the device never gives a wrong answer. Right? It might say, I don't know, but otherwise it doesn't give a wrong answer. Right? Okay, so these are the conditions. So here we have some linear constraints. And, well, basically, so this F variable here, you could take F1, F2. Because of this condition, F0 follows from that. Well, actually, let's do that. And all the matrices, so X, all the matrix elements of F1 and F2. Well, actually, to include the linear constraints, we would have to add a few more pieces to this matrix. But this is, of course, written as a block decomposition. We have zeros in the other positions. Right? So these matrices are clearly linear functions of their matrix elements. In the matrix, I took the x's to be real. Now these are typically complex, so you have to take real and imaginary part. But then it's clear that this is a parameterization of the constraint matrix, of the inequalities. There's an additional part for the equalities here. And then you can just turn the crank and solve that with a semi-definite numericals program. Right? So for the moment, I'm only interested in identifying some problems that can be solved using this kind of problem. or or that fit into this problem type. Okay. Next one would be entanglement detection. So given row state on each Alice tensor H bar, show that row cannot be written okay, let's keep it to, okay. So this would be a separable state, that is a non-entangled state. And now I just give you all the matrix elements of row and ask you, can I write it like that or can I not? Right? Now this is a hard problem, and it's actually in a bad complexity class, so it's not easy to decide, although, and especially when you're close to the separable border, so then it can be quite tricky. So here I'm using a necessary criterion for entanglement and testing that. Right? So the necessary criterion is that, so the criterion that would allow this conclusion, show that it cannot be written, and the criterion that would allow to say something like that is there is no state row n on H Alice tensor H bar tensor n. So now Alice is put together with n bobs, or whatever the names are, such that the trace H bar 1, well, not H bar K, H bar N. So I'm tracing out, so this is a state on from n plus 1 system, and I'm tracing out all the bobs except one, number K. Right? So this would be, I take this row n, and that would be a state on HA tensor HB, and the condition is that this is equal to rho. Right? Okay, so this is a sequence of semi-definite infeasibility problems, right? I would set it up like I would introduce the infeasibility as an additional variable, and then ask for, well, the conditions here are the positivity of rho n. This has to be a positive matrix. And then there are linear constraints. All these are linear constraints on rho n. So I can phrase that as a semi-definite problem immediately. Right? So I don't even have to introduce, like here, I don't even have to introduce variables x in a complicated way. I can just directly go to these matrices and solve this infeasibility problem. And so why is that a criterion, by the way? Because if rho is separable, then it follows that rho n, you just take sum lambda I, rho Alice I, tensor rho Bob I, and you just tensor that n times with itself. This is exactly the monogamy motif, right? So this means that the kind of correlation that is sitting in the state rho is utterly non-monogamous, right? So no matter how large n, I can always find such an extension. And this would be just saying that I have a non-monogamous or shareable kind of correlation in this state. Shareable was the term that was used by Van Schumacher when he introduced this. And it turns so a state for which such an extension exists would be called n-shareable, and infinity shareable actually is equivalent to entanglement. So this is a set of criteria that sort of approximates the separable set from the outside. Okay. So, but in all these cases, the positivity, the fact that this is a semi-definite problem, directly comes from the interpretation of states and observables. Okay, what else do I have? Let me see. Code optimization. So, n would be a noisy channel. That is given. Let's say from H into H out. And we would like to and also given a dimension for the kind of signal that we want to transmit. And so find an encoding. So if I write, okay, let me do the usual thing here. Writing Heisenberg picture, okay. And so E would be the encoding that would go from H in. So that would be the output of the encoding is something that feeds into that channel. And let's just call this space H without anything. And D is a decoding that would go from D of H, D of H out. So H is some Hilbert space, right? And then I can look at decoding, the noise, and an encoding. This would be a channel from D of H to D of H. Right? D goes, oh shit. Encoding and decoding are the other way around, so it actually spells end. Okay. So D goes from H to H out, then we go from out to in with N, and then we go from in back to H. Okay. So this is a channel on the overall mapping on the states of one system, and the task is to find these guys, E and D, so that E and D is as close as possible to the identity. So I know what the noise is, so this is the assumption here, and the degree of approximation we need some numerical criterion on that, and in order to fit that into the semi-definite form, it's best to have one number that we stick to that. And this would be the channel fidelity. As it's sometimes called. And this is simply computed by taking this channel, tensoring it to the identity, applying it to a maximally entangled state, or vector, and evaluating with another maximally entangled thing. So this is on the same space, so this is also same space H. Right? This quantity is equal to 1 if and only if this one-dimensional projection gets mapped precisely to itself, and then this is 1. So we're actually looking at the fidelity kind criteria. So, and we would like this to be maximum. Now, why is that a semi-definite program? Well, not just like that, because E and D are the variables here. So on the one hand, this is kind of nice, because the variables, well, what is the constraint on a channel? I can characterize the channel in terms of its Choi matrix, and then the channel is completely positive, if and only if the Choi matrix is positive definite. Positive semi-definite. So clearly we have a semi-definite constraint and some linear constraints, namely that the Choi matrix, or the trace of the partial trace of the Choi matrix has to be the identity. Right? Has to be what I get from this state directly. Right? So there's a linear constraint and a positivity constraint, and that gives you the set of channels directly. Right? So the set of channels satisfies the kind of criterion, but unfortunately, this functional is bilinear. Right? So it's linear in E and it's linear in D, but not jointly linear in these variables. So there is a bit of a problem. But one way to do that is the following. We want to maximize the fidelity, so given the decoding, I optimize the encoding, and given the encoding, I maximize the decoding. And so I alternate these steps, so we get and then in each step I will improve the fidelity. And each single step I have a linear functional over positive definite constraints, so this is a semi-definite program. This works quite nicely for moderate size matrices. That is, if the dimension for the noise is kind of manageable, but for example, if you take the 5-bit code, then H in and H out would be 5 qubits, and the input would be 1 qubit. Then you could do this on a PC. Well, I guess a bit more than that. So a few more bits are okay, but if you try to do this on 10 bits, this explodes exponentially. And although semi-definite programs have a relatively good behavior in terms of dimension, if the dimension goes up exponentially, the problem becomes exponentially harder. So the semi-definite, we'll see how this is actually done, what the algorithm does. But if the dimension really becomes exponentially large, this becomes exponentially hard. Right? So it would be good behavior in terms of the dimension, but not beyond that. Okay, so more problems. Well, we have all kinds of problems here. Right? So many problems in quantum information theory where something has to be optimized are actually semi-definite programs. And for some time, actually, people felt that if you reduce something to a semi-definite program, then you've basically solved your problem. Well, this is true for moderate dimensions, but for really high dimensional problems and coding problems, you would like to to solve in very high dimension. Right? This is, of course, also not possible with this method. Right? So if you want to define something like a channel capacity, where you want to look at the coding of long blocks of qubits, and actually asymptotically long blocks of qubits, no numerical method will give you that. You have to think about how to organize your codes, and you can't do that with this direct ab initio optimization. Actually, it turns out that for not too large noise, the 5-bit code is optimal. We have a little paper about that from around 2000. Michael Reinhard was a PhD student who did that. We had another method. We actually didn't solve the semi-definite problem, but had another method of doing that, which was, I guess, in this case, equally fast. Okay, so I just mentioned a few CP norms. So we looked at several different norms. For example, the norm of complete boundedness in the last lecture, and actually computing that can be cast in the form of a semi-definite program. There are different ways of doing that, actually. So measuring uncertainty bounds. We have just recently we produced a semi-definite program to solve those. All kinds of things. So many things can be done like that. And of course the reason is that quantum information is full of instances of this positive cone, or the positive semi-definite cone, so actually almost very many problems are of that form. Okay, so let me, I hope that is enough for motivation. We might actually solve this guy on paper, looking at the dual problem as well. That might be an interesting exercise. Okay, let me erase this. Okay, so associate with every semi-definite program, written like that, so now we can use this black bar, is a dual. Well, it's again a semi-definite one. Program. It's the following. So you're supposed to maximize something now with respect to Z. which is going to be a matrix of the same dimension as these F matrices. Right? And the quantity that we maximize is actually minus the trace F naught Z. Right? And this is subject to some linear constraints. And the constraints are that trace Fi, so for all I, trace Fiz is equal to Ci, where Ci is a constant that is in the target functional of the primal problem. So when we call this a dual problem, we have to have a name for that other one. So this is now called the primal problem. Right? So there's a set of linear constraints, and the important semi-definite constraint is that this matrix Z itself be positive. So there are two target functionals here. This thing, in terms of Z, it's also linear, of course. The basic constraint is linear constraints and a semi-definite constraint, right? So it's a semi-definite problem. So there will be some maximal value of this quantity, and there will be a minimal value of that, the other quantity. And the point of all these duality statements is that they are closely related. Right? In fact, let us write this sum Ci xi. So let us now take x to be a feasible vector, a feasible set of variables. That is, it satisfies the constraint there, the positive semi-definite constraint. And let's take z to be feasible in this sense. Right? So it satisfies these constraints. So if that is true, we can take the Ci here and write this as the sum xi trace Fiz. But the sum xi fi is actually closely related to this f of x, so it's f of x minus f naught actually. Right? So this is equal to the trace, or let's split that already, minus trace f naught z plus trace z f of x. Okay, we should have this z always in the back, but it doesn't matter. Right? Okay, so there's a simple relation between the target functionals, those are these two. They differ by this term. Now, the z is positive, and so is this f of x, according to the feasibility conditions. So we have the trace over two positive matrices, so this is positive. Right? So we conclude that this thing, the target functional of the dual problem, is less than the target functional of the primal problem, no matter what feasible points I insert. Right? So now the task for the dual problem is to maximize this, and the task for the primal problem is to minimize that. Right? So this implies that the solution of the dual problem, let's call that D star for dual, this is the soup of these values, is less than or equal to the inf of these values. And let's call that the solution, or the optimal value for the primal problem. So the dual is always less than the primal. This is just follows directly from the definitions. That is also always one part of the duality statement. And the important theorem in this game is that these are the same. If Well, not always actually, and it's interesting to look at the counterexamples, but there's a condition. So if either one of the following holds, and so the primal problem is strictly feasible. That is, there exists some vector x, so that f of x is not only semi-definite but really definite. That is, the matrix is strictly positive, which means it has no eigenvalue 0. Right? All the eigenvalues are strictly positive. And so the same, right? Same condition, strictly feasible, which means there exists a z so that z is positive, strictly positive, and of course satisfies the linear constraints. Right? So this is part of a general duality theorem. Actually, if both of these are actually often quite easy to check. Right? If both hold, so if 1 and 2, both problems are strictly feasible, then both are attained. So I was writing this soup at an inf here, but of course you have many problems where the supremum, where you can compute the supremum, but there's not actually an element in the set that attains that. That's actually the point of defining the supremum, or the distinction between the supremum and the maximum. Right? So actually, if you have both these feasibility conditions, then you know that there will actually be an x and a z, so that you have equality. Now, this is basically just an adaptation of a general convexity result in convex optimization, and I will not prove that. So although it's interesting, right? So there's some nice convex geometry and separation theorems for convex sets that go into that, but I won't do that here. Right? But this is the basic criterion, and often it's very simple to satisfy. Actually, this rewrite of a feasibility, so you have to solve the feasibility problems first, if you want to check that. Right? So if you're just giving numerical versions of this problem, then you might want to decide the feasibility like this. So this is clearly strictly feasible, right? Because if you just increase s a little bit more, you get a strictly feasible. I mean, any x can be strictly is s. For any x, you can find an s so that the pair is strictly feasible. So this is clearly falls in that in the good class. So you can use this to reliably compute the best s, and that might be negative. That would mean that there's actually a strictly positive bound, so you would immediately have strictly feasible points. Okay, now I think for the rest I wanted to tell you how these semi-definite solvers actually work. So there's not one algorithm, there are various variants of that, but they have common features. So So let's say, so here's some set, some convex set, and a linear or an affine functional on that set has constancy planes like that. So this is a convex constraint set. And this is these are lines where the target functional is constant, right? Of course, you have to think of this in considerably larger dimension. So, and then the solution would be out here, right? Because if these are increasing values in this direction, then you would actually, this is the point that you're actually looking for. So we're maximizing an affine functional over a convex set. So, for example, this set could be a polygon or a polyhedron. Right? That would mean a body that is the convex hull of finitely many extreme points and is therefore also bounded by finitely many faces, hyperplanes, maximal faces. So finitely many hyperplanes would enclose that set, and there is a traditional algorithm that solves that sort of problem. It's called the simplex algorithm, where you try to move in any direction as far as you can until you hit one of the constraints. And then you're in the boundary. So then you have a problem in a smaller set in the boundary. But then actually the face that you hit on your first trip might actually not contain the absolute minimum. So when you found the minimum so you're decreasing the dimension, and then if you hit it in an extreme point, you have to see whether you can switch to another face to make it better. Right? So this is basically the simplex algorithm. The philosophy is move around on the boundary. So the modern algorithms, even for that problem for which the simplex algorithm was originally designed, are completely different. They are called interior point methods. Right? So which means you try to stay away from the boundary. You do the exact opposite of the simplex algorithm. So you stay away from the boundary, and I'll tell you how to do that using a barrier function. And going along something called the central path. So how can you make sure that you're sitting inside the convex? So the barrier function, call that phi. You typically want that to be convex. Right? So from did we have a name for that convex set? Call it, I guess the only possible letter for that is C. Right? So it's allowed to take infinite values, and it's supposed to be convex. And well, actually, it's a function on whatever Rn on the ambient space, and phi of x is infinite when you hit the boundary. So it diverges towards the boundary. So if I have this kind of I tried to copy this convex set, right? It was basically horseshoe sort of thing. So then the level sets of the barrier function would be, so these are level sets. And for a convex function, the level sets are also convex. So it would have a minimum somewhere in there. Oops, bad, convex. So, and then there is a minimum somewhere in the center. Right? It doesn't really matter what that is. So, the strategy is, and let me just draw one of these lines from before, right? So the target. So strategy. Minimize phi. Phi of x, but with respect to x, subject to. I should have given a name to the target, right? So the target function is like t of x. Right? Well, let me call that value tau. Right? So you fix some value tau. And then you minimize your target function over that. So why is that easy? Well, it's not necessarily easy, right? Depends on the barrier function actually. So and you do this using Newton's algorithm. I'll remind you a little bit of how Newton's algorithm works in high dimension. Right? Of course, we need that in high dimension. Okay. Now this brings you to some point. In this picture, it would be the one where you're lowest. Do we have a colored chart? Yes, we have red. Okay. So you would be here, and for other values, you would be sitting somewhere at some other point, right? Now, and then you move around here until you hit. Well, actually, this curve is parameterized by the value of the target function. So, if you have to minimize, you will just decrease that step by step until you actually hit the boundary. And so solution, let's say, is x of tau, right? And you call this the parameterized central path. Of course, there is a certain trade-off, right? You have to you go to the central path, and then you walk along the central path, right? So you take this as a starting value, of course, for your next minimization and your next value of tau. And then, so that one of the features of Newton's algorithm is that in the end it converges awfully fast, right? So there would be a trade-off by maybe not doing the full Newton iteration and just get a somewhat better point, and then starting your next value from there. So you have like a tube around the central path, which you have to hit, and there are various criteria for how good you have to be. And then from there you can do your next iteration by changing the parameter on the central path and going in this way, going a bit closer to the maximum. Right? Now, this can be absolutely horrible. Right? So I described a very general setting with a convex set. If the convex set is complicated and the barrier function is complicated, this doesn't help at all, because this is a crazy thing to do. Right? So for example, I mean, there are well-known, nice finite dimensional convex sets over which a minimization is extremely difficult. For example, take the set of restrictions to two neighboring points of all translation invariant states on an infinite chain. Okay, so you have a one-dimensional system, and you look at a translation invariant state, all very well-defined concepts, and you look at the reduced state to just two neighbors. Now, in terms of those, you can write down the expectation value of any nearest neighbor interaction. So you can actually, minimizing a linear there's a linear functional on this set that gives you directly the minimum for an interacting many-body system with nearest neighbor interactions. This is all you have to know in order to compute the average density, and that's the thing that you want to minimize. Right? So there is a nice linear functional on this convex set, but minimizing a general linear functional on that set is exactly as hard as computing the ground state of an arbitrary nearest neighbor interaction, which is damn hard. We know that this is hard. Moral is that this convex set, although it looks, if you make a picture of it, it looks pretty harmless. But if you are going to the details of the boundary, it has all the intricacy of one-dimensional ground state problems. And that is pretty bad. So a convex set might be very complicated. Then it might also be the case that you don't find a good barrier function. What's a good barrier function? Well, that is one where this minimization works nicely. Newton's algorithm, and we'll talk about that, requires you to compute the first and the second derivative of this function. So you need a barrier function that has a simple to compute derivative, up to second derivatives. That's the real headache, right? To find a barrier function that expresses this convex set well and still has a nicely computable derivative. There's also another thing that would be good to have, namely when you're marching along the central path, you would like to know how far away you are. For example, so there's also in this general convex setting, there is a dual problem always. And so if for every point on the central path, you would automatically get one, well, I can't really point there because this is in a different space, but automatically get a dual feasible point, so that these will converge to each other. So actually you can use that as a measure of how far you're away from the maximum, and you would terminate the algorithm when the duality gap becomes smaller than epsilon. Right? So if the duality gap would be this quantity, right? The difference between the two. If that is zero, then you know you've hit the solution, and if this is very small, you will be satisfied with numerical solution. Okay, so three things you would like to have. Well, a good first derivative, a good second derivative, and a way to determine a dual feasible point. Okay, and all this works. So for semi-definite, there exists a barrier function with easily computed first and second derivative. And it also gives us dual feasible. I'll show you the thing about the dual feasible form. And so this barrier function has to express the constraints. Right? So C is the geometrical object here, and the kind of constraints that we have are just positive definiteness of matrices. Right? So So we said phi of x is minus the log of the determinant of f of x. Of course, this depends on the problem. Huh? But the matrix that has to be positive is stuck in here. So the determinant will be positive, and we now will have to compute these derivatives. Okay, so well, this is a standard computation. Do you know the derivative of that function by heart? Well, we know the inner derivative. Yeah? So f is actually has these fi as gradient vectors, and so we really have to compute log det x plus epsilon y, where epsilon is just a parameter now, right? And y, well, some fixed matrix. And so we are in the interior, so we can assume that x is strictly positive. So this whole machinery works when we have a strictly feasible point, right? And that will be our starting point. Any strictly feasible point is where we start. Then you can compute on which hyperplane you are, and from that hyperplane you go to the minimum, that is, you go to the central path. Okay, I promised you also to talk a bit about Newton's algorithm, but that's not forgotten. Okay, so we have to do a Taylor expansion of this guy in epsilon. So let's take the derivative of that. Right? Now, the derivative of a log is 1 over the determinant of x. Well, let's say at epsilon is equal to 0. Right? Then we have the determinant of x times the derivative of, let's say, the derivative just of the determinant. Now I can take this constant factor inside, because it doesn't depend on epsilon, and then dividing out the determinant means that I actually can take the inverse of the matrix inside. So this is d by the epsilon of x to the minus 1. Remember, x is strictly positive, so we can invert. X minus 1, x plus epsilon 1. So this is, and the determinant. Okay, so of course we can simplify that a bit. This is d by the epsilon. The determinant of 1 plus epsilon x minus 1y. Okay? So this is a standard computation, for example, when you show that Liouville measure is conserved, you need that, and in various places in physics you need that. So let's just look at the determinant, which is a sum of, these are finite matrices, right? So this is a sum of n factorial terms, and each term means going through the lines of the matrix and picking one element from each line that corresponds to a permutation, multiplying with the sign of the permutation, and adding the whole chunk. So now what terms do we get in zeroth order? This is the identity, and then there's small stuff around. So if you take, the leading term, of course, is just the identity. That's 1. Then the next leading term is one where you pick a term up, the linear term would be one where you pick up one order epsilon term and nothing else. Now, as soon as you have a permutation, a proper permutation, then you will get 2 terms epsilon, at least, in their product. So you will have a term of order epsilon squared. So the linear term means you just have to look at the identity permutation. So, and then you just expanding, you see that this is just the sum of the diagonal elements of this additional matrix. Okay, so this derivative is equal to, at epsilon equal to 0, is equal to the trace of x minus 1, 1. We also need the second derivative. So this is easily computed, right? So you take this in this application. You are somewhere on the way of solving your problem. The f of x will have to be computed anyway, and this would just mean that you have to invert it, and this directly gives you the gradient, right? So if you, of course, now the partial derivatives with respect to x would be just, and then the y would be just one of the fi's, right? But we'll spell that out. So next, so of course I can continue like that. This derivative will be true when I put x plus epsilon y here. So now I would like to take the first derivative of this guy in order to take the next derivative of this expression. So I would like to expand that linearly in epsilon. So if these were numbers, you would get x minus 1 plus, well, the first derivative of this guy is 1 over x squared. And but this would be, well, for example, if these are Hermitian matrices, then the product 1 over x squared times y wouldn't be good. So you have the x and y don't have to commute, of course, right? This is the difficulty here. It turns out that this symmetrized way of writing the derivative is good enough, right? This is actually the correct derivative plus order epsilon squared, right? Order epsilon squared. So we actually have the second derivative. Now, why is that true? Okay, so where's the equation? I want to prove that, right? And we'll do that quick and dirty by multiplying this whole equation by the inverse of the left-hand side, but that is by x plus epsilon y, right? So if we look at this expression, x minus 1 plus epsilon x minus 1 y x minus 1 times x plus epsilon y. This should be 1. This should be 1 to order epsilon squared if we got the derivative right. Right? And so let's just multiply it out. Here's the 1. Then we have the linear terms, that is plus x minus 1y, epsilon, x minus 1y, this, of course, this is wrong. If these were numbers, this would be wrong. So, right, the derivative of 1 over x is negative. So, that should be minus here. So if we multiply this stuff out, this is minus x minus 1 y, x minus 1 x. This is 1, so this part is 0. So we have order epsilon squared for the rest. Right? That's something. So, so if we divide this equation that we just computed by this thing, and this is order 1 because as epsilon goes to 0, this converges to x. Right? So, so we get that the equation is correct. Okay. Usually computing the derivative of a matrix-valued function can be a pain, right? Because of all this non-commutativity, but 1 over x is a very simple function where this works. Right? So actually computing the derivative of the exponential looks much more difficult because of the non-commutativity of these matrices. Okay, so this means that log det, or minus log det f of x, well, let's say f of x plus epsilon y is, so this is the phi of x plus epsilon y, right? So this will be phi of x plus epsilon sum. So the y term are the deviations here. So y, the sum over epsilon yi trace x minus 1, f of x minus 1, fi plus epsilon squared sum ij. What do we have? Yi, yj, trace, and now we put in the second derivative, right? So we have the first derivative, and to compute then we just have to compute the derivative of the first derivative to get the second. So this will just be trace f of x minus 1, fi f of x minus 1, fj plus order epsilon cubed. Right? So this is the second derivative that we need for the Newton method. Right? So we have to do this only along the hyperplane where we don't change the constraint. Right? So but this means that we don't take a minimum over all y's, but only those y's that have f naught expectation 0. Right? But let me just comment a little bit on the Newton method. Right? So Newton's algorithm would be something minimize phi by iterating minimize second order approximation to phi. Right? So that's the basic idea. So if we can compute the derivative, so if we have, so the algorithm would start at some value of x, then compute, let's say psi I at the point x at where we are. Right? Well, let's say you call this call this x, right? And call this a. Well, H maybe is a good one, which is the matrix of second derivatives. That's the thing that we just wrote there, right? And so we know how to compute that and do this with a simple matrix computation. We have to invert this f of x at that point. We have to do that anyway. And then this is very quick to compute. Okay, so now then we know that phi of x is roughly, or is equal, let's say, to phi, let's say phi of x plus a small y is phi of x plus psi scalar product with y plus 1/2 y a y. Okay? So now here it's important that the barrier function phi is actually convex, so that this matrix there is positive definite. Well, it is, right? You can just see that. And so this is just the convexity of the function that you're targeting in this step. So A is positive. H is called the Hessian. Like the poor guys that were sold as soldiers from the state of Hessen. So Hessian. So this is, let's call this phi 2, right? So this is the second order approximation. And we have to compute the minimum of that. Well, that's easy. So the minimum of phi 2. Right, so this is a generalized parabola with quadratic form h. And so we can just take the gradient here. So gradient with respect to y gives psi is so gradient phi 2 is the same as the gradient of phi, of course, which is psi plus hy. Yeah, so you put that equal to 0. So we see that y has to be h minus 1 psi, and then you just stick that in. And so this is solving a linear equation, right? That's what you need for that. Once you have this Hessian matrix. Okay, and this converges if the convex function is nice. That is locally pretty much looks like a parabola or like a quadratic function. Then this is a very good step. And like the one-dimensional thing that you know for solving equations or computing square roots, this is quadratically convergent. That is, in every step you double the number of digits that are right. This is extremely fast. So actually, in their discussion, I was using the book of Boyd and Vandenberge, a nice book on convex optimization. They have a special article on semi-definite as well. And they say, well, there is this trade-off. How many iterations of the Newton method do you do before you go along the central path? And they say, well, the difference between going close to the central path and actually getting on it is just 1 or 2 iterations of Newton. So you might as well do it. So the difference between getting close and getting very, very, very close is almost negligible. So actually most algorithms, they say, I can't really tell, actually go very close to the central path to move on. Okay, there's one more thing. The dual feasible point. So I'll just sketch that. We've computed the derivative. Have we? Here it is, right? So now we have to do a minimization problem with constraints that we could put in by a Lagrange multiplier, right? Because we are only going along this hyperplane. And if we add that constraint, then we actually see that the matrix F inverse is a dual feasible Z. Well, actually, so we have f of x inverse 1 over Lagrange multiplier is actually satisfies the linear constraints, is also obviously positive, and therefore is a dual feasible point. And what they show is that this is sort of as a shadow of the central path going to the maximum. There's a dual of the central path, so you know how far away you are from the maximum. This is a very convenient feature that most barrier functions that you can dream up probably don't have. But this is a little bonus that comes out of the semi-definite structure. Okay, yeah, are there questions? We have a few minutes. Where can you get this? So maybe you can tell us. There are various semi-definite solvers on the market, running, for example, under MATLAB and some other platforms. Mathematica doesn't have a good semi-definite solver, apparently, or does it? No.
I don't know. I just used it from MATLAB because David
used MATLAB, and you're using MATLAB also, right? Right. So, okay. So you see in our group, semi-definite problems are being solved all the time, actually. Well, then you basically rely on a solver. I haven't tried to write one myself, but these are the basic steps. Okay, so thanks for your attention. So then my proposal would be for the exercise section, we'll look at some simple semi-definite programs and solve them on paper, or one maybe, or two, not very many. Solve that on paper and also computing the dual, right? So that you get a feeling of how this duality works. And that will be tomorrow at 12, right? Okay, so see you then.